evening. Has anyone noticed my voice being too soft in the recording with the new setup? Is it okay? Okay. Because I vaguely remember somebody mentioning that. All right. All right, so we are back to big and little o, omega, and theta. And I think last time we stopped with the discussion of limits. So we're going to restart from supremum and infinitum. I changed the notes a little bit. I added just a little bit, to the whole thing. So it's not a whole lot, just a little bit. All right, so we'll start with section 3.1, okay, which we started last time, but we'll restart from this particular place. And we'll magnify this a little bit. Okay, that looks better. All right, so the key here is we have a set X, which is a subset of A, and then we want to define a predicate P on a particular value of Y. And the key here is Y doesn't have to be in X. Y can be outside of the set X. So when we define P of Y using this notation here, which basically says, P of Y is true if and only if for all X, lowercase x in uppercase X, such that X is less than or equal to Y. So that means Y is at least as large as every element in X. And that's basically saying Y is an upper bound of X as a set. So we are talking about uppercase X as a set. So P of Y is basically saying Y is an upper bound of X as a set. Is that part okay? So if P of Y is true, then Y is an upper bound. But you can find an upper bound, for, that is not particularly useful. So I'll give you an example. So today what we'll do is we'll use more examples to illustrate the concepts. So if I define P of Y the same way as here, then we'll go ahead and take a look at what happens when we define X with certain specific examples. So I'm going to define X as, let's say, 1, 2, 3, and 4. Okay. So in this case, P as a predicate on a particular value, let's say 10, is what? What is P of 10? P is still defined the same way as before. P of something means that thing is an upper bound of the set that we have specifically defined here. So is P of 10 true or false? It's true, because 10 is greater than or equal to 1, 10 is greater than or equal to 2, 10 is greater than or equal to 3, 10 is greater than or equal to 4. Okay, so P of 10 is true. But wait, we can find something else that is also true. P of 9 is also true. Okay, so you can look at this and go like, what about P of 5? That is true too. What about P of 4? Yep. So in this particular case, P of 4 is also true, but that's the smallest value that will make P true. So that makes it the minimum of the minimum of the upper bound. Is that okay? So 4 is the minimum upper bound, assuming X is defined the way that we define here. Is that okay? All right. So we'll say here, 4 is the minimum upper bound of X. Because you cannot find me another value that is less than 4 that can still make the predicate P true. Is that okay? So within everything that can make the predicate P true, this is the smallest. Is that good so far? So we give it a special name. Okay, so 4 is called the supremum of X in this case. In terms of notation, we say 4 is SUP for supremum of the set X here. So when we use SUP as an abbreviation of supremum, it is always applied to a set. In this case, X is a set. Is that okay? The number of elements in the set where you're taking the supreme num form doesn't have to be finite. In this case, it is finite. Okay, it doesn't have to be finite. So are we good so far with the definition or the understanding of what is a supremum? Supremum is the minimum upper bound of a particular set. All right. So now the next thing is going to be the infinitum. So when you look at the definition of infinitum, it's basically the opposite. So when you look at the predicate Q, Q is the opposite of P. So if P is the upper bound of a set X, Q is saying it is the lower bound of a particular set X. Is that okay? So we'll switch back to the example. And then we'll keep using this same X here. And then we'll say, what about Q of 10? Q of 10 is false, because it is definitely 10 is not the lower bound of the set 1, 2, 3, 4. It's not even less than or equal to any one of those. I mean, it cannot possibly be the lower bound. Okay. So what about Q of -3? Oh yeah, that'll work. It's a lower bound. But is it the maximum lower bound? Is this the lower bound that we cannot increase any further? No, not quite, because Q of -2 is also true. So that makes -3 definitely not the maximum of the lower bounds, because -3 is a lower bound, -2 is also a lower bound. So -3 is definitely not the maximum of the lower bounds. Is that okay? So we keep increasing the value, okay, assuming they can only be integers, which they don't have to be. So we get to Q of 0, and we say, yep, that's true too, because 0 is definitely a lower bound of the set X. And then we go like, but wait, there's one more. Q of 1 is also true. But then we cannot increase anymore. If we increase from 1, that value will no longer be the lower bound of this particular set X. So that means the value 1 is the maximum lower bound of this particular set X. Is that okay? Yep.
So is it going to always be always the lowest and highest number for the infinitum and the
Not necessarily. Yeah.
just like
Well, because the set can be infinite.
oh, okay.
Yeah. So when the set is infinite, then it becomes, sometimes it's challenging, a little bit interesting to find out, how we can define that number. And besides, we have a few more sections to go. So infinitum and supremum are only tools that we need in order to get to some of the other terms that we need to define. So these are still building blocks of what we need. All right, so that makes 1 equal to the infinitum of X. So the notation to say that is INF for infinitum. So 1 is the infinitum of the set X. Once again, infinitum and supremum apply to sets. Okay? So 1 is asking about what is the minimum upper bound of a set. The other one is asking about the opposite, which is the maximum lower bound of a set. Is that okay? And the minimum requirement is the set has to be partially ordered. Doesn't have to be totally ordered, but it has to be partially ordered. So are we good so far? Understanding the definition of supremum and infinitum. Infimum versus supremum. Okay. And I'm not sure whether we talked about limits or not. I think so. The next one is actually limit of a sequence, so we'll deal with that next. So when we deal with a limit, this is getting back to pre-calc, okay? So we have a lot of gibberish here, okay? The gibberish is basically saying, if I use this notation, which is affirming, which is saying that if you take the limit of I to infinity, and that limit of xi is k. What does that mean? Well, it means this is going to be true. What is going to be true again? If you find me any non-zero or any epsilon that is greater than 0, I can find you an m, such that m is an integer. Okay? What about that integer? Every single j that is greater than or equal to m, and j itself has to be a natural number, will have this particular property. What property? The absolute value of k minus x of j, x, by the way, is a series. K minus x of j is going to be less than epsilon. Does that resemble something that you learned from pre-calc? I mean, if I have to name one thing in this class where, okay, yeah, taking pre-calc is going to help, this is it. Everything else is just algebra. This is the place where pre-calc actually applies. What does that mean? So that means you can make epsilon really, really small. Okay, you can start with 0.5. Okay, and depending on what function what series we are talking about, with epsilon being 0.5, you might find that m has to be at least 500. Okay, so x500, k minus x500 is going to be less than epsilon. K minus x of 501 is going to be less than epsilon. In fact, if you look at everything to the right-hand side of x500, k minus x500, when you take the absolute value of that, is going to be less than epsilon. Okay, so if I can find that m for 0.5, what about if I divide it by 5, if I divide epsilon by 5, so the epsilon is now 0.1, I bet you cannot find that m anymore. Nope. If this works, that means, m only has to be bigger. I just have to look further down the series and say, everything from here on, okay, maybe m has to be 2,000 this time. So x of 2,000, x of 2001, x of 2002, x of 2003, and all the way to the right-hand side. If you subtract those numbers from k, the absolute value is guaranteed to be less than epsilon. And that's with epsilon being 0.5. Okay, if I make epsilon 0.01, I bet you cannot do that. Not if this is true. If that is true, you can make epsilon as small as possible, as long as it is not 0 itself. I can still find you an m, a particular m, so that when you look at the series, x of that particular m and forward is going to be less than epsilon away from k. Is that concept okay? It's a little bit abstract, but at the same time, what it is really looking for is, what is that series converging to? It's looking for convergence. Are we doing okay so far with this or not? Good? Okay. So what about graphically? Can we look at this in a graphical way? Because I think the visual can be very helpful in this case. So let's go ahead and see if we can look at this from a visual perspective. I'm going to discard that. Start with a new one. So if you have a series that has this particular shape, and it just kind of go up and down a little bit, kind of like that. So assuming the fluctuation is going to decrease as we go on, that means they're converging. Okay, so in this case, visually, okay, I'm not doing a very good job, writing this, drawing this picture. So basically, if you think about it, k is probably here. This is our k. So what is epsilon? Well, epsilon is something that you choose. Okay, give me an epsilon. Oh, I want to make epsilon. Okay, I'm just using an example here. I want to make epsilon here, and because epsilon has to be above and below k. So if I make epsilon, okay, let me indicate where epsilon is. This is epsilon. Okay. So if I make that epsilon then the first number in the series that meets this requirement, it's probably about here. But everything to the right-hand side of this will meet that requirement as well. Is that okay? What if I make the epsilon even smaller? Okay, what if I make the epsilon half the size that it currently is? Well, in that case, maybe we have to get up to here, and then every point after this is going to meet that requirement. What if I make the epsilon even smaller? Well, we just have to do it further down the road. But given any type of non-zero epsilon, I can find one point in the entire series so that is the starting point where every single point after that is within that margin that you have specified. That is what it means when we say, when you take the limit of I to infinity, x of I equals to k, means exactly that. Is that okay? But then there are series that are not, they're not converging. Okay, I'll give you an example. So we'll take a look at this particular example where I define x of I to be -1 to the power of I. Okay, and I starts from 0, and I has to be a natural number. So that means x of 0 is 1, x of 1 is -1, x of 2 is 1 again, x of 3 is -1 again. It just alternates between 1 and -1, right? If that is my series, I cannot claim that there's no limit, okay? There's no, it doesn't approach a particular value. Because in this case, we are talking about a function. If you look at the line, it is like this. It's a square wave, right? If it is a square wave, then I can no longer claim and say, give me an epsilon. Okay, I'll give you an epsilon. I'll give you an epsilon about yay big. Where is the first number in the entire series where the value of the x is within that margin, and everything after that is going to be less than, is also going to be within that margin? There's no place, okay? So as a result, this thing has no, it does not converge. Some functions converge, and some functions, like this one, does not converge. Are we doing okay so far with this concept? Okay. So in continuous math, sine and cosine are kind of like this. They do not converge because, the sine wave just keeps going like this. So the concept of having or not having a convergence has nothing to do with whether it's continuous or discrete. So are we doing okay so far with that? Okay. So we have a special case when the limit is infinity. So in the case when I say a series approaches infinity, it means the following. For all y in the real number set, there exists an m in n such that if you look at any number at j or after, it's going to be greater than y. Are we okay with this concept? Now, it doesn't seem like much, right? It's like, okay, but what does that mean? Well, that means the function is at least monotonic. It keeps going up. It doesn't fluctuate. It doesn't go up and down. Because if it ever goes down, then this requirement may not be satisfied anymore. So it basically goes either always up, or at least it stays the same and then it goes up. It's a non-decreasing function. We have to at least know that much. And then the second thing is, if you go further down the line, the value does go up. It doesn't stabilize at a particular point. Is that okay? So with a series that looks like this, where it converges to infinity, then you can no longer say that it has one particular value that it converges to, which also means that you cannot find the infimum or the supremum in such a series. It doesn't make sense to ask, oh, so with this series, what is the maximum lower bound? Well, you can find the lower bound, but not the upper bound in this case. So it doesn't make sense to ask what is the minimum upper bound, because well, the further you go down the line, the higher the value. So you can never really find a single minimum upper bound in the case when the series approaches infinity. Is that okay? Now, you might say, but what is the practical application of this concept? I mean, are we going to use any series that look like this? Yes. Okay. So later on, these are all tools so that we can have discussions later on about algorithm complexity. Do you guys still remember the context of all of this discussion? Algorithm complexity, how much time it takes for an algorithm to finish relative to the size of the problem. Remember that competition between Pat and me, who gets to pack up and go? Yep. Okay. Binary search versus linear search. Okay. So we want to develop some kind of notation, some kind of tools, so that we can quantify and evaluate algorithms. We can compare algorithms. Okay. So we'll get to that part. It's just that we have a little bit more definitions to go. So now we have limit superior, which makes use of Infinim and also supremum. So when you look at this, the definition of the limit superior of a series x, where n goes to infinity, is this. What is that? Well, if you look at the nested definition, it means we are using Infinim on the outside. In other words, we are taking the maximum lower bound of. Okay, well, when we use Infinim, it has to be applicable. It has to be applied to a set. So what is in that particular set? Each element in that set is itself a supremum. What kind of supremum are we talking about? So when you expand this, okay, it becomes something like this. So the first element of, well, I shouldn't say first element, but when n equals to 0, the element that we'd be looking at would be supremum of xk, where k is greater than or equal to 0. So starting from 0, what is the minimum upper bound of the series, including x of 0? Okay, you take that value, and that becomes the first element of the set that you apply Infinim to. What about when n equals to 1? Okay, because n is greater than or equal to 0 is really just a condition to limit what kind of values can apply to n. So when n equals to 1, then we are looking at the supremum of x of k, where k is greater than or equal to 1. What does that mean? Well, we are taking the minimum upper bound of x1, x2, x3, and x4, and so on, but we are excluding x0. x0 is no longer included in this element. Is that okay? What about when n equals to 2? Well, when n equals to 2, that means we are taking the supremum of x of k when k is greater than or equal to 2. What does that mean? That means we're excluding x0, we're excluding x1. From x2, x3, x4, and so on, what is the minimum upper bound? So we are taking the minimum upper bound in steps. And then we take all of those minimum upper bounds, and then we ask, of all of these minimum upper bounds, what is the maximum lower bound of that? Yep.
So in essence, you're taking an infinite set of delta matrices, an average set on delta matrices, and then you're saying what is the largest delta in that set?
Not exactly. Maybe a picture would help. Okay? So we'll take a look at a picture. And let's see. My palm touched the screen before my pen did, so. Okay, there we go. So this time we'll take a look at something that looks like this. And then the oscillation does not stop anymore, okay? It just kind of keeps going. So when you look at when you look at this point here, when I is here, okay, not I, but n. So when n is here, what is the minimum upper bound? The minimum upper bound is right here. Is that okay? So you take note of that minimum upper bound, and you say, oh, okay, the minimum upper bound is here. And then you take the minimum upper bound and say, what about when we are talking about here? Now remember, the minimum upper bound applies to that point and every single point to its right-hand side. So when you look at the minimum upper bound of the second point here, well, I think the minimum upper bound is about here. Okay, so we'll click that here. Okay. What about when it's here? Well, when you look at that, the minimum upper bound from this point on is not actually here, because it's actually here. Because remember, the minimum upper bound does not apply to just that point itself. It applies to every single point and after that point. So we are looking at the curve of the remaining portion to the right-hand side. And to the remaining of the right-hand side, this is the highest point. So that becomes your minimum upper bound of when you start from this point here. So we take all of those minimum upper bounds, okay? So all the minimum upper bounds is going to be kind of all here, because you can see the curve, the lowest point of the curve is about here. But everything after that is still higher. So the minimum upper bound is set by that. So now you take all of these minimum upper bounds and say, what is the maximum lower bound of all of these things? Well, the maximum lower bound is really just whatever. So you're moving a point, okay, from way below everything, and then you start to move it up, move up, until it starts to touch the first point. Well, that point here becomes the maximum lower bound of all of the minimum upper bounds. So I will just kind of point out which point we are talking about. So we are talking about this thing here. That becomes the maximum lower bound of all of the minimum upper bounds. Is that okay? Yes? The most important point to remember is when we take the minimum upper bounds, we are taking the minimum upper bounds from a particular value I and everything after that too. But we are moving that starting point, as we go through this set. So according to this picture, what do you think is going to be the limit inferior? We just talked about the limit superior. And what about the limit inferior? It's defined exactly the opposite. Okay? So when you look at limit inferior, okay, scroll down, it's exactly the opposite of limit superior. So now the individual smaller points that you're dealing with, they are the maximum upper bounds. Then the maximum lower bounds, the maximum lower bounds, you collect all of those things, and then you ask, what is the minimum upper bound of all those points? That answer becomes the limit inferior. So let's go back to that picture and try to figure out, in that particular picture, what that value is supposed to be. So when we get back to this picture, so we'll take this point here, okay? If n is here, what is the maximum lower bound? In other words, if I start from here, where is the lowest point of this entire sequence? I think it's there. Is that making any sense? All right, so we'll make a note of that. And we say there's one here, and then we just keep going, okay? Then the second question is, what if I start here? Okay, so I'll make a point, denote that, and say what if I start here? What if n is this place here? In other words, I'm asking, what is the maximum lower bound of the remaining part of the curve to the right hand side of this point? This is not it, okay? I think this is it. Is that okay? So now we make a note of that and go like, okay, so we have another data point. And what about if I start, what if I start here? What if this is the end we are talking about? So if I consider this point and everything to its right hand side, where is the maximum lower bound? This is not it. No. Oh, okay, I think that's it. So now we have the maximum lower bound relative to this index position being here, and then we make a note of that. So we are collecting all of these maximum lower bounds. So in the end, we have all of these things here, and then we look at all of those maximum lower bounds within these points, and then we ask the outer question, which is, of all of these things, which one is our minimum upper bound? Minimum upper bound means you can start with a point that is outside of every single point here, and then you keep moving it down until it touches at least one of them. That becomes your minimum upper bound of the maximum lower bounds. Is that okay? Okay, let me point out first. So this one is limit superior. This one is limit inferior. Do you see how this works? So the nice thing about limit superior and limit inferior is it will work on x of I being -1 to the power of I. Remember that square function thing where it doesn't really approach a particular value? I can still find its limit superior, it's just 1. I can still find its limit inferior, it's -1. So that forms an envelope, okay, that tells me the behavior of that particular sequence as the sequence goes on to infinity. Because that's what we're trying to figure out. We're trying to figure out the behavior of a sequence when it keeps going and going to infinity. Is that okay? So, so the normal limit is great if your function has a limit. But sometimes it doesn't. Sometimes it oscillates. So there's no particular value that it settles on. So now you cannot have a limit. Well, but even without a limit, we can still define what is a limit superior and what is a limit inferior. So we can still define an envelope to define, to characterize the behavior of the function as the series goes on to infinity. So are we okay with this discussion so far or not? Because I don't want to just talk about the definition of those terms, but also why they are important or what they are for. So limit inferior and limit superior is a pair to help us define an envelope. This becomes the envelope. So if I draw the picture, if I draw the envelope itself, so that means if I extend this envelope out to infinity, so imagine these two lines just keeps going and going and going to infinity. That means eventually everything after a certain point in the series will fall between these two lines. It will fall between the line of the limit superior and the limit inferior. And that's good because that helps me define the behavior of the series as it approaches, as the sequence number, the index number approaches infinity. Yep.
A simple way to look at it is just like the smallest hill and the shallowest valley.
It's the lowest hill And the shallowest valley. Yes, that would be a great way to describe it. Thank you. I'm not that much of an outdoor person. But it's great. I mean, that analogy is great. I like it. Yep, go ahead. Oh, okay. All right. So are we good so far with all these terms? But you can see how Infinim and Supremum are really just tools so that we can get here. Yep.
So it creates like an envelope, but what's the envelope?
The envelope, well, that in return is going to be used later on.
Okay.
So all of these tools are building up to bigger and bigger, or concepts that are closer and closer to what we need to express. Yep.
Why would that one with the smallest peak be the? Why would that be considered a maximum? Because if you look to the right, there's other maximums to the right.
Well, the picture is, but we don't know what is going on here after that. Oh, you mean the upper bound?
Yeah, like the upper, like right next to it, there's a higher peak. So wouldn't that be considered the?
Well, remember, this line is representing the limit superior, which is defined by further things down the line. So if you extend the series indefinitely, what is that? What is the maximum? No, yeah. What is the maximum lower bound of the the minimum upper bound of those points? But you're applying that, as we go on in this entire series. So we are just kind of using this to kind of project the function will kind of keep oscillating, but it will keep oscillating within that range. Is that okay? Yep. Okay. All right. Switching back to the notes here. So now we can finally define the big O notation. I mean, some of you have heard of the big O notation. When you look up various algorithms on Wikipedia, they also define what is the big O notation. But the big O notation actually has a very specific mathematical definition. It is this thing here. So as it turns out, the big O notation by itself is a set. Okay, so big O of g of n consists of all the functions, so that if f of n is an element of big O of g of n, if and only if the following is true. Is that okay? So big O of g of n itself is a set of functions. And every single one of those functions as a member of big O of g of n has to satisfy this requirement. What requirement are we talking about? The limit superior of the ratio between of f of n divided by g of n has to be less than infinity. Yep.
I don't understand less than infinity.
It means it is not infinity.
And is it like
Hmm?
real number?
It means it has to be a specific number. Is that okay? So the next line actually says that. The English translation of this is there exists some kind of value k so that g of k times g of n is greater than or equal to f of n. Is that okay? The interesting part is you have to say for all n, because when n is different, this k can be different. Are we still doing okay so far or not? Because this is why we have to define all of those terms: infinum, supremum, limit inferior, limit superior, limit inferior. All of those terms, led to this notation, led to the big O notation. Let's take a look at an example. Okay, so we'll look at an example, And this one I think I can use Notepad. Let's see, do I have a Notepad here? Yep. I'll just get rid of this stuff. So we'll define f of n, okay? Now, f of n is defining the actual time that it takes for an algorithm to finish relative to the size of the problem. And n is the size of the problem. So it can be the size of an array, the number of vertices, the number of edges. It has to be some kind of metric that you use to measure the size of the problem. Okay, how big of a problem are we trying to solve? That is captured by n. So in this case, let's say it's an array, okay? And we'll say, this is like 2 times 2.5, exactly 2.5, plus 1.75 times n plus 0.3 times n squared. Okay? That is the exact definition of f of n. And let's just say that this is the amount of time it will take to bubble sort an array of size n on my exact computer. Okay? So this is quite exact. The question now is, well, that's a pretty ugly number, and it depends on which computer we are talking about. Because, if it's running on a faster computer, some of these constants will change. Even the ratio between the constants can change depending on, well, does it have really a good caching mechanism? Does it have a large cache, small cache? Does it have DDR4 technology? Does it have this and does it have that? So even the ratio between those constants, 2.5, 1.75, and 0.3, can shift and change depending on the characteristic of the computer that you're using to run the bubble sort algorithm. Is that okay? So that makes comparison a little bit kind of challenging. So now the big question is, well, can we simplify this to something that's a lot easier to look at so that we can compare between algorithms? So the proposal is, well, let's see if I can make g of n just n squared. Look at this. F of n is kind of complex, and g of n is, easy. So the question now is, can this particular g of n be serving as the upper bound of f of n? So we look at the ratio between these two. Okay. So now we ask this question. So we define x of, I'm going to use x underscore I to be x subscript I. Okay. So x subscript I is now defined to be f of I divided by g of I. That's how we define the series. So x underscore 200, x subscript 200 is f of 200 divided by g of 200. Is that okay? These are just definitions, so there's no particular reasoning behind that. But this is how we define the series. So the next thing we want to do is to look at the behavior of this series. So now we're looking at the limit superior as I goes to infinity. And what we are looking at is, what is this series going to look like as we compute its limit superior. Limit inferior defines the lower bound, and limit superior defines the upper bound. So what do you think this is going to look like? It's closer and closer to 0.3. Because when you look at it, okay, so let's do some divisions here. So we are looking at the 2.5 divided by n squared. As n becomes really, 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 really large, okay, what is that value going to be? It's going to get closer and closer and closer to 0. So it becomes kind of negligible at some point. What about 1.75 n divided by n squared? Well, you simplify it, right? You cancel the n. So now it actually just becomes 1.75 divided by n. When n becomes really large, what's going to happen to that term? It's going to approach 0 as well. Okay, so it becomes negligible at some point. And then you look at the last term, which is 0.3 times n squared divided by n squared. N squared cancels out n squared. So as n approaches infinity, in fact, whatever n it is, doesn't matter. It is always 0.3. Is that okay? So when you look at that, okay, so the limit superior of x underscore I is in this particular case 0.3. Okay, so the question is, can I use g of n as defined here as the upper bound of f of n? Does it meet the requirement? Is the limit superior less than infinity? Is 0.3 as a particular real number value less than infinity? Yes. Okay, cool. So that means this particular g of n can serve as the upper bound of f of n. Is that okay? But what about, yeah, go ahead. Yes, because in that case, you will have the limit superior becomes 0, and 0 is less than infinity. Yes, so absolutely, that's a good point, and it's important to note that too. So in this case, okay, if you look at, so I'm gonna use h of n here. So if h of n is n to the power of 3, okay, then when you take that limit superior, so I'm gonna have to do this here. I cannot use x anymore because I have the ratio needs a new name. So y of I is now f of I divided by h of I. Okay. So when you look at the limit superior of this one of y, it will become 0. Does that make sense? Because every single term, 2.5 divided by n cubed, is going to approach 0. 1.75 n divided by n cubed is going to approach 0. Even the largest term, which is 0.3 times n squared, is going to approach 0 when you divide it by n cubed. So every single term is going to approach 0, which means the entire series, the series itself, is approaching 0. But I don't really care whether it is 0 or 5 or 20. I only need to know, is that a particular value? Because if it is less than infinity. Yep, it is 0 is less than infinity. So that means, if you use h of n, which is n cubed, that can also be used as an upper bound. Are we overestimating a little bit here? Yeah, but it's still an upper bound of the complexity of the algorithm. Because upper bound doesn't mean it has to be matching the function itself. It simply means it has to be more than the function. It's at least that much. Okay? The reason why sometimes we're interested in just the upper bound, even though it is overestimating, is because, but it gives us some idea. Okay, it gives us the worst case scenario of how long it's going to take. And sometimes, that is enough. So are we okay so far with the concept of big O? Okay, so in this case, what we say is f of n is an element of big O of g of n. F of n is also an element of big O of h of n. So big O is a notation that gives you a set of functions. And you're basically asking about membership of that big O notation. If a function is a member of a big O of another function, that means the function within the big O notation can serve as an overestimate or an upper bound of the function that you're estimating. Is that concept okay? All right. Very good. And now we look at the other definitions. So we have the upper bound, which is using the big O notation, which is also by far the most used notation. Because when you look at every sorting algorithm, search algorithm, and stuff like that, people keep asking about, what is the big O of this particular function? Because it serves as the upper bound of the time computation time of a particular algorithm. Little o is known as negligible, and when you look at the definition, it says when we take the limit as n approaches infinity, is the ratio going to 0? If it does, then we say f of n or g of n is a gross overestimate of f of n. So n cubed is an overestimate of that f that we had before. But it is still an big O, so both big O and little o would apply to n cubed. But only big O would apply to n squared with the f that we have defined in the example. Is that okay? Because one has the series converging at 0.3, the other one has the series converging at 0. The one that has the series converging at 0 is going to be have a little o notation, but both would have the big O notation applicable because they are both less than infinity. Is that okay? Little o is not used that much. So now we have the lower bound definition. The lower bound definition is looking at the ratio again, and this time it's asking, well, is it at least 0? Well, excuse me, let me take it back. At least 0 means it's greater than or equal to 0. This one is greater than 0. It can be infinity, but it has to be greater than 0. So what it means is g of n is not a gross overestimate of f of n. Because if g of n is a gross overestimate of f of n, this will become 0. The fact that it is non-zero, that it is greater than 0, means it is not a gross overestimate. Are we doing okay so far? It can be a gross underestimate. So in the case of, okay, I'll give you an example of a gross underestimate. So we are keeping this f of n here, okay? We got g, h, and then I, j, k. We can use k. So we'll define k of n as a constant. So when k of n is a constant, well, that's the simplest constant I can think of, just 1. Is that okay? So when you look at k of n being 1, what is going to happen to f of n divided by k of n as n approaches infinity? The series is going to approach infinity. Okay, so let me write it down here. Okay. So the bottom line is when you look at the and this one applies to limit inferior. So when we look at, okay, it's my Fitbit interfering with my computer. Did I talk about this? Yep. So limit inferior as n approaches infinity, and this time we define, we got xy already, so we'll use z. So z of I is defined to be f of n divided by f of I divided by k of I in this case. So when we look at this series, z of I, the limit inferior is going to be what? It's going to go to infinity. Does that make sense? Okay, so if this is making sense, does it meet the requirement? Does it meet the requirement that the limit inferior is greater than 0? Is infinity greater than 0? Yes. Okay, so that means we can now use that notation. This is the big omega notation. Oops, backspace, wrong place. Okay, so now we can use the big omega notation. Let me change the size of this window because people in the back may not be able to see the entire thing. There we go. So now we can use the big omega notation where we say f of n is an element of big omega. I can't really use the omega symbol here, so I have to spell out omega. Is a member of big omega of k of n. Meaning that k of n is a lower bound of f of n. Because the limit inferior is greater than 0. Hold on a second here. We saw something a little bit earlier where the limit superior is 0.3. So let's go back to that one and see if the limit inferior is also going to be 0.3. So let's go back, and I'm just going to copy and paste a little bit of material here. It was this guy here. So I'm going to copy this much stuff to the bottom here. And then I change limit superior to limit inferior. And we are trying to answer the question, what is that? F of n is still the same thing. It has a constant plus n times something plus n squared times something. It's still that, okay? G of n is the way we defined a little bit earlier. I just kind of copied and pasted it. X of I is still the same as before. It is the series of the ratio between f of I and g of I, okay? But this time, instead of looking at limit superior, we're looking at limit inferior. Where is that going? Go ahead. It will still be 0.3. Not 1 over 0.3. It is still exactly 0.3. Okay? It is still exactly 0.3. Oh. Okay. Is 0.3 greater than 0? Yes, it is. So now we can also make that conclusion that f of n is also in big omega of g of n. In other words, g of n, which is just n squared, is also a lower bound function of f of n. But I thought it was an upper bound. Yes, it was, and it is. So it's both. So g of n, being defined as n squared, is both the upper bound and the lower bound of f of n. Can something really serve both purposes? Yes, and we like that. Because now it is actually telling us the whole story. It is not grossly overestimating where the series approaches 0 itself. It's not grossly underestimating where the series goes to infinity. It is right where we want it. Okay, it is approximating the curve of f of n as more accurately as n increases. Is that okay? So this is actually what we are looking for. We are looking for something that is both the upper bound and the lower bound of the exact time complexity of an algorithm. Is that okay? Are there any questions about these concepts? That's the big O notation. That's the big omega notation. Yep.
What do you have a different limb in compared to its limb here?
So is there any point where limit inferior and limit superior are different? Let me think.
Would you have like a probabilistic algorithm?
So sometimes it doesn't take much time to get to the answer, and other times it takes a lot of time to get to the answer. I suppose if you have a series that fluctuates, that keeps fluctuating even as the series goes to infinity, then the limit superior and the limit inferior will be different. So you will have so the two of them will form the envelope of the numbers that will fall in within that envelope as the series goes on forever. But in time complexity, we usually do not have algorithms that will fluctuate. At least they'll not fluctuate indefinitely. So they might fluctuate, but eventually they will settle. They will actually approach a particular value. So it's unlikely that we will see something that where the limit inferior and the limit superior will be different. Okay, so that was a good question. Any other questions? Well, if a function is both the upper bound and the lower bound because it is so desirable, don't you think it deserves another Greek symbol? I would think so. Okay, we like to give things specific names. Okay, so in this case, we'll also say that if f of n is in big O of g of n, and f of n is also in big omega of g of n, then, well, I should say if and only if. So if and only if, double F, then we say f of n is in big theta of g of n. So big theta is the good stuff that we really want, okay? If we can find, a g of n that f of n is in the big theta of g of n, that means we have hit the jackpot. We have a function that closely estimates the actual amount of time that it takes to execute an algorithm. That's what we want. So in this particular case, g of n indeed is big theta, because n squared is closely estimating the shape of the curve of our f of n. Our f of n is not exactly a square, but it has that component. So as n gets larger and larger and larger, then the two curves becomes almost exactly the same, with only a scaling difference in between, which is 0.3 in this case. Is that okay? All right. There are certain algorithms where the best case behavior is different from the worst case behavior. Quicksort is one of them. Let's see, what else? I think quicksort is one. I cannot think of another one. So this one is dominant. It's a small omega notation. So this one is really just saying, little omega or lowercase omega is saying, when f of n divided by g of n, when n approaches infinity, then the series is also going to approach infinity. That will make g of n the dominant function of g of n. It's a gross underestimate of f of n. Kind of makes sense, right? Now remember, this one, in order to qualify to be a dominant, it has to be a lower bound first, because lower bound sets the limit inferior is greater than 0, right? This one is saying the limit is approaching infinity. So anything that meets the requirement of dominant is automatically a lower bound, but not the other way around. Is that okay? Because what this means is f of n, which is the actual amount of time for the algorithm to finish, is going to grow faster, much faster. Well, not much faster, but it's going to grow faster than g of n. So g of n is grossly underestimating the amount of time to execute the algorithm. So are we good so far with the terms? And then the last one, which is what we call a type bound, is something that we have seen already. This is what big theta is about. So f of n is an element of big theta of g of n, if and only if f of n is an element of big O of g of n, and f of n is also an element of big omega of g of n. So it is both, so g of n is both the upper bound and the lower bound. It cannot possibly be grossly overestimating, and it cannot possibly be grossly underestimating either in this case. So are we doing okay so far with these concepts? More or less. All right. Okay, so I'm going to give you a mind map, okay, a concept map. And start a new page. All right, so I'm going to give you a concept map here. We will start with inferior, superior, and limit. Okay, that's just a normal limit. So those are the very first concepts that we talked about in this particular module. Okay, and then from Infinim and supremum, we start to understand what is limit inferior and limit superior. So so the arrow is indicating concept dependency. Is that okay? Now remember, but you also have to remember that limit inferior and limit superior do not depend on the concept of limit, because they don't have an epsilon involved in here. Okay? So from these concepts, we start to define, in the case of superior, we define the big O notation, which is a upper bound of the time. So I think upper bound has to do with limit inferior being, okay, let me switch back to the notes just to be sure. This is limit superior of f of n divided by g of n. So this concept leads to the definition of big O. This concept leads to the definition of big omega. So when we have big omega and big O, they combine to big theta. Is that okay? And then little o which is negligible, is based on limit, and the same thing about dominant. So little o and little omega are based on limit. So limit leads to small o, and it also leads to lowercase omega. So are there any questions about these concepts? You know, how someone's taking a picture. I need to get a little Darth Vader mask. Whenever I see a camera coming up, it goes like that. So is that kind of helping to map out, you know, how the concepts, you know, map out? Yep.
I have a very general question.
Mm-hmm.
Asymptotic analysis only makes sense as a number as n goes to infinity. Given that, why do we look at the worst case running time of an algorithm instead of the average case running time of an algorithm, since it's a number?
That's a very good question. Okay, so the question was, why do we look at the upper bound and the lower bound, but not the average case? So the answer is, in order to compute an average, you have to know the distribution. So how often does the case goes to the worst case? How often does it go to the best case? How often is it somewhere in between? So until you know the distribution of your problem sets, you cannot really compute the average.
So this is about general analysis.
This means given only the algorithm itself, not knowing the actual distribution of the data of the problems, you can still define all of these terms.
You just assume the worst because that's the average it is. The worst is better than that given a certain.
Correct. So typically what we really want, if possible, is we can get to big theta. Because big theta is not about average, it's not about the best case, it's not about the worst case, it is the exact, okay? So we want to get to big theta if it is possible. So in the case of a lot of common algorithms, like bubble sort is n squared, and it's big theta n squared, which means it is both the upper bound and the lower bound, which is what we want. If you look at binary search, it is big theta of log of n, when n is the size of the array. And once again, it is both the upper bound and the lower bound. When you look at quicksort, there are variations of quicksort, but I think in one particular variation, it has a different upper bound versus the lower bound. I believe the lower bound is n log n with quicksort, but the upper bound of that particular version of quicksort can be n squared. So that one has a different big O compared to the big omega. Big omega is n log n, and then big O is n squared. So what we are really trying to do, in addition to knowing the big O, big theta, or the big omega of a particular algorithm, we want to be able to compare different algorithms. So you can compare bubble sort versus insertion sort. They are both big. They are both big theta of n squared. So that means, yeah, sometimes one may edge out the other one, but that's just a constant. Okay, it's just a ratio. It doesn't really change much, over the size of the problem. But when you compare merge sort, which has n log n as a big theta, versus bubble sort, which has n squared as big theta, then it's a big question. That it's really clear which one is better. So with algorithms of the same big theta that belong to the same big theta, then you go like, well, okay, we need to look at other considerations to select one or the other. Okay, so in the case of n log n sorting algorithms, merge sort is the one that is superb when you are working on slow medium, especially things that do not have random access. We talked about that last time. Whereas quick sort, or at least one variation of quick sort, can be done in memory in place. Okay, so that's kind of cool. Okay, so now it depends on the application and not the time complexity anymore. So is that kind of answering your question? Okay. The same thing about linear search, which has a big theta of n itself is linear, as opposed to binary search, which is big theta of log of n. So in that case, there's no question. Even though binary search is slightly more complex when it comes to the algorithm itself, the time complexity is way superior to linear search. So is that kind of helping you guys understand, what these terms are for? Basically what is the purpose, as opposed to the actual definition, which is kind of mechanical and dry and boring. Is that okay? What do you think is the upper bound, or can someone give me a upper bound of the A star algorithm? Since we are kind of talking about that sort of stuff. Well, okay, so in this case, you have to define what is n. How do you define the complexity, or how do you define the size of a problem when you're talking about a graph? Because a graph has two components. It has got vertices and it has got edges. So you can have a really weird graph where you have like 20 gazillion vertices but no edges. So if you have a graph that has no edges, it doesn't take any time to finish it, because the set omega is going to be empty to begin with. So you're done. Okay. So what do you think is going to affect the amount of time it takes for A star to finish? Number of edges. The number of edges is far more important than the number of vertices. Then the second question is, okay, do you think A star will revisit an edge more than once? It does. Okay. But what about Dijkstra's algorithm? Dijkstra's algorithm will never visit an edge more than once. So with Dijkstra's algorithm, the big O is just going to be the cardinality of E. The number of edges forms the upper bound of Dijkstra's algorithm. But with A star, that's not the case. The worst case, depending on how crooked your heuristic function is, can actually exceed the cardinality of E, because we can potentially revisit an edge more than once. But the exact number I cannot remember, but it's worse than the cardinality of E. So why do we even investigate A star when its worst case is actually worse than Dijkstra's algorithm? Well, the best case is potentially better because you can doctor the H function so that it is the exact length of the shortest path. Okay, then it will only visit vertices along the shortest path. So then yes, absolutely, you can doctor that. So the average case is, you can think of, or your H function is reasonable. Okay, but it's hard to quantify or qualify what is quote unquote reasonable in that case, because there is one qualification, so the A star cannot or will not revisit the same vertex. If the heuristic function is monotonic, then it is not going to revisit the same edge. So if you can satisfy that one extra requirement, then the time complexity, or at least the upper bound of A star, will now become the cardinality of E again. But if your heuristic function does not satisfy that requirement, then you can potentially revisit the same edge more than once. Then the upper bound is no longer just bar E bar. Is that okay? Okay. All right. So we are done with today's lecture. I do want to show you what we're going to talk about on Wednesday, because the semester is wrapping up. So when this is done, the next topic is right under this one. So we are starting to analyze time complexity, which is generally speaking pretty difficult. This is an upper division kind of topic. So the next topic that we'll be visiting is not even, we'll talk about complexity again, but only when we get to the third item. The second item is really just to talk about recursive definitions and algorithms. Then we will combine these two topics to talk about the third one, which is called the master theorem. I think we will definitely be able to get this done in the next class on Wednesday, and then we might be able to get started with this topic on Wednesday. Okay, so you might want to kind of read this one. This is not very difficult. It's really just a matter of how do we look at algorithms? How do we look at recursive algorithms? What makes something recursive, recursive? It breaks a big problem into smaller problems, but each smaller problem has the same nature as the original problem. It's just smaller, and that's why we can perform recursion and recursively solve the problem. Okay, and then based on how many pieces you break it into, how much work you have to put into to break it apart and then merge the answers back together, that will in return influence the time complexity. If a problem only gets smaller, and it remains as one piece, like binary search, then the time complexity is going to be very small. On the other hand, if you break it up into two pieces, but the sum of the two pieces is the same size as the original one, then you will not be looking at a very big reduction in terms of time complexity. If it takes a lot of work to break it down into smaller problems, and the sum of the smaller problems is the same as the original problem, then you're looking at a pretty bad time complexity. Okay, so that's the stuff that we'll be talking about on the third point. So when you have time, please read this particular module and understand the concept. If you do not understand some of the concepts, you can bring it up in an email. I can go over those topics in class, or bring the question to class if you want to. Okay, so let's get it done by Wednesday, because these are fundamental concepts for the later stuff.